right, 5.4a, exponential functions. There we go. All right, so exponential functions and natural logarithms. We dealt with natural logarithms prior to break, right? And so the relationship between a natural logarithm and e to the x are inverses of one another. We just dealt with inverses. What's an inverse again? It's a what? A switch in x and y. So that's why these topics go together so well. So if I natural log e to the x, I get x. If I e natural log x, I end up getting x. They are inverse operations of one another. Now, a quick little history lesson. E was first discovered by Leonard Euler back in 1731 when he talked to his bro, Christian. All right. So it's been around for over almost 300 years to give high school and college people pain. All right, pretty good. All right, let's do some Algebra 2/pre-calc. So I have 7 is equal to e to the x plus 1, and I need to solve for x. So what do I need to do to both sides? I natural log it. All right, that's my inverse operation. So now I have natural log of 7 is equal to x plus 1. And then how do I start solving for x? I need to do what? Subtract 1. So now I have natural log of 7 minus 1 is equal to x. Then I want to put this into my handy dandy calculator. How many are we going to round to? 4 decimals.
0.9459.
All right. 0.9459. All right, pretty good in the hood? All right, let's keep moving. So now I have natural log of the quantity 2x minus 3 is equal to 5, and I need to get to x. How do I get inside that natural logarithm? I exponentiate both sides. So now on my left side, I'd end up with 2x minus 3 is equal to what?
E to the fifth.
E to the 5th power. All right. And then how do I start solving for x? We can do these 2 steps at once. Let's do it. What do? We add 3 and then what? Divide by 2. So now I have x is equal to e to the 5th plus 3 over 2. So let's put it in our handy dandy calculator. And T to the J is going to give it to me. Skipper, what do we get?
75.706.
All right. Good. All right. Real quick, we also need to talk about a little bit of exponential rules. If I have the same base, so my base is e, if I have things being multiplied, what happens to those exponents? They add. If I have things with the same bases being divided, in this case e, they need to be what?
Subtracted.
The exponents are subtracted. Now, I need you to have a basic understanding of what e to the x looks like. E to the x is very fast moving, right? It's exponentially growing. Now, can I ever get a negative on e to the x? No, unless it's shifted vertically, it's not going to be negative. All right? It's always going to cross where unless shifted? 0, 1, because e to the power of 0 is 1. All right? And so we need to have that basic understanding of e to the x. Pretty good? All right. Now, let's move on to some calculus. Now, this is the toughest derivative we're going to have. So bust out your note card. If f of x is equal to e to the x, the derivative is equal to e to the x. All right. If I have e to the x, f prime is e to the x. All right. Everybody got that? All right. It's pretty simple. However, what rule can we never forget? Chain rule. All right. Guess what's going to happen in pretty much all of these? The chain rule. All right, let's put it into practice. Here we go. So I need to derive, with respect to x, e to the 2x minus 1. All right. So if I have e to the 2x minus 1, well, the derivative of that will also be e to the 2x minus 1. However, what rule can't we forget? Chain rule. So what pops out? A 2. So my derivative is 2e to the 2x minus 1. Pretty simple. All right, let's look at this next one. So now I have e to the negative 3 over x. And I want to derive this with respect to x again. So what is my derivative? E to the Negative 3 over x. However, I also need to take the derivative of negative 3 over x. So what is my derivative of negative 3 over x? 3 over x squared. And by now, you should be very comfortable in doing that. This is an x to the negative first. The negative 1 comes down. We subtract, so we get negative 2. We throw it to the basement. All right? All right. Let's keep moving. So now we're going to find relative extrema of this function. So my function is x e to the x, and I want to find a relative extrema. So we're going back to chapter 3. We're going to use those things again. What does it mean to have a relative extrema? What do I need to first find? A critical number. How do I find a critical number? Take a derivative set equals 0. So let's take a derivative. All right. So what rule are we going to need to use here? X and e to the x are being what? They're being multiplied. So what rule do we need? The product rule. So what's the derivative of my first? 1. And then times e to the x. Plus the derivative of my second, which is e to the x, times my first of x. All right. And eventually I'm going to set that thing equal to 0. But what could I do before I even set it equal to 0? I can factor out what? E to the x. So I'm going to factor out e to the x. And then I have 1 plus x. And I'm going to set that equal to 0. Now, this e to the x thing, is that ever going to be 0? No, it will never be 0. So I can't actually set that equal to 0. It won't do me any good. So now I set 1 plus x equal to 0. So when do I get it? I get x equals negative 1. That is my critical number. What should we do to find a relative extrema, though? I do what? I need to do my sign chart. Exactly. So I need to go from negative infinity to negative 1, and then negative 1 to infinity. All right. And again, if I substitute something on this interval, let's pick like negative 2 sounds great. Is this part ever going to be negative? No. However, if I substitute a negative 2 right here, that part's going to be negative. So f prime is less than 0. And then I substitute something on the interval negative 1 to infinity, like 0 sounds good. So f prime would be what? Positive. What did I just create? I have a relative what? Minimum. At negative 1 comma something. Now, how do I get that something? Substitute back in what? The original. So now I do f of negative 1. So I'd have negative 1 times e to the negative first power. This is my childhood. So what happens to this e to the negative 1? It goes to the basement. So I end up having a relative minimum at negative 1 over, comma, negative 1 over e. And so that is where I have my relative minimum. Pretty good?
Negative 0.3679.
All right, fantastic. All right, let's keep moving. So now we're going to deal with the bell curve. All right, so we're going to use the bell curve here. Now, I told you before, other sciences and math just steal from calculus, and that's okay. We just do it. All right, they can do whatever they want. So in statistics, you learn that one standard deviation has 95%. That's fine. All right, that's good. However, guess where that little bell curve came from? Calculus. All right. And so actually I had a student before, Ryan Spivey. He would actually do the calculus and not do it the stats way. It was kind of cool. So anyway.
Did it work every time?
Yeah. Because guess where it came from? Calculus. All right. So anyway, here we go. So what it really is, what the standard deviation or the normal probability, the bell curve, is this function. So I'd like you to write out the function. We have 1 over square root 2 pi e to the negative x squared over 2. And I want to figure out the points of inflection. I want to verify that my points of inflection are at positive and negative 1. All right, that's all we're going to really do with it, but this is actually where it comes from. All right, cool. So how do I get a point of inflection? I need to take a second derivative. But before we get to second derivative, I need to take a first derivative. Now, this 1 over square root 2 pi, that's just a number. It's a constant multiple. It's just a number. So that's just going to chill out front for us. So I have 1 over square root 2 pi. And then I need to take the derivative of this e to the negative x squared over 2. So the derivative is e to the negative x squared over 2. However, what pops out by the chain rule? A negative x. All right, a negative x pops out. And then I need to take a what? A second derivative. And again, this 1 over square root 2 pi thing, that just stays out front. And then what rule's happening with this part? This e to the negative x squared over 2 times negative x. That's a what? A product rule. So the derivative of my first ends up being what? E to the negative x squared over 2 times negative x times the second, which is negative x. And then plus, what's the derivative of my second? Negative 1 times the first of e to the negative x squared over 2. And so what could we factor out of that part? What can we factor out of this part right here? The e to the negative x squared over 2. So my f double prime is equal to 1 over square root 2 pi times e to the negative x squared over 2, and then times what's left? X squared minus 1. And now what am I going to do with this portion? I'm going to set that equal to 0. Now, the 1 over square root 2 pi, that's not going to really matter. It's just a number. This e thing, is that ever going to be 0? No.
But
so
that
really, this x squared minus 1, if we set that equal to 0, when do we get our p-poise? X equals negative 1 and x equals 1. Now, technically, should we check for a sign change? Yes, it's going to work. So we really just found p-poise. I don't want to deal with it. All right, pretty good? All right, fantastic. Ben, go ahead and read.
The number y of shares traded in millions on the New York Stock Exchange from 1990 through 2005 can be modeled by y equals 39,811 e to the 0.1715 t, where t represents the year with t equals 0 corresponding to 1990. At what rate was the number of shares traded changing in 2000?
All right. At what rate was the number of shares changing in 2000? How do I get a rate? Take a derivative. Exactly. So how do I notate taking a derivative of that function? dy dt, because it's with respect to time. All right. So now I still have this 39,811. The derivative of e is just e to the 0.1715 t, right? However, what happens? A 0.1715 pops out. All right, so there's my derivative. And what do I want to evaluate that derivative at? At 10. Why is it 10? Because it's 10 years after what? 1990. So I want to say dy dt at time equals 10. And then I bust that thing into my handy dandy calculator. Elijah, what do we get?
I got 6,500.
I think that's what we got.
I got
37,938.6 what?
6827.
827?
No,
All right.
6827.
All right, fantastic. Now, what are my units here?
Dollars.
No.
Shares per year.
Millions of shares per year.
That's crazy. That's a lot. That's a lot of shares.
All right. So
That's
we
a lot
need
of
to
shares
understand
created.
our units. If we have millions of shares and it's represented in years, that would be our derivative. Okay, pretty good. If I had to take a second derivative, for some reason I had to figure out how the rate of the rate is changing, then what would be my units? Million of shares per year per year. All right. There you go. Page 358, numbers 2 through 16, every other even. All right, that's pre-calc or algebra 2, round to 4 decimals. And then we start taking derivatives of e to the x. However, what can we not forget? The chain rule. All right, product, power rule, those things are going to happen as well. However, chain rule is going to be in like everything. All right.